This time around we're going to start our discussion about muscle physiology. There's actually two sets of events that go on for a muscle contraction to occur. There are the actual events for the muscle contraction, and then there are also the events that are set forth stimulate the muscle to contract. That would be the electrical events that come down the nerve, the axon, and stimulate the sarcolemma to send the electrical event down the surface of the sarcolemma and deep down through those triads that we were looking at. When the electrical event hits those triads, we will see that there are electrical stimulated gates there that will open, that will allow calcium to flow out into the surface of where the myofibrils are and trigger the contraction. But first, let's take a look at the contraction. Then we'll take a look at the electrical activities that are involved to stimulate the contraction. And then we'll put them together, hopefully, in what we call the excitation-contraction coupling events. Now, when we're talking about contraction events, what are we actually talking about? We are talking about the fact that the muscle cell will shorten. Not only will the muscle cell shorten, but the myofibrils will also shorten. Because remember, the myofibrils are the individual units that are found inside of that muscle cell. Now, if you remember, we have a functional unit within that muscle cell that we measure the level of contraction, and that unit is called a sarcomere. And remember, a sarcomere goes from one Z disc to the next Z disc. And so when we see the contraction, the Z disc will actually come closer together. And what's happening there is the thin filament made of actin is actually sliding over the surface of the thick filament, the myosin molecule. So in that case, that's what we call a sliding filament mechanism when the thin slides over the surface of the thick. But as always, there are things that you cannot say. The thin and the thick filaments do not themselves shorten. They simply slide over the surface of one another back and forth over the surface.
Action of the skeletal muscle generates the force necessary to move the skeleton. A contraction is triggered by a series of molecular events known as the cross-bridge cycle. In a skeletal muscle fiber, the functional unit of contraction is called the sarcomere. A sarcomere shortens when myosin heads and thick myofilaments form cross bridges with actin molecules and thin myofilaments. The formation of a cross bridge is initiated when calcium ions, released from the sarcoplasmic reticulum, bind to troponin. This binding causes troponin to change shape. Tropomyosin moves away from the myosin binding sites on actin, allowing the myosin head to bind actin and form a cross bridge. Also note that the myosin head must be activated before a cross-bridge cycle can begin. This occurs when ATP binds to the myosin head and is hydrolyzed to ADP and inorganic phosphate. The energy liberated from the hydrolysis of ATP activates the myosin head, forcing it into the cocked position. A cross-bridge cycle may be divided into 4 steps. Step 1. Cross-bridge formation. The activated myosin head binds to actin, forming a cross-bridge. Inorganic phosphate is released, and the bond between myosin and actin becomes stronger. Step 2. The power stroke. ADP is released, and the activated myosin head pivots, sliding the thin myofilament toward the center of the sarcomere. Step 3. Cross-bridge detachment. When another ATP binds to the myosin head, the link between the myosin head and actin weakens, and the myosin head detaches. Step 4. Reactivation of the myosin head. ATP is hydrolyzed to ADP and inorganic phosphate. The energy released during hydrolysis reactivates the myosin head, returning it to the cocked position. As long as the binding sites on actin remain exposed, the cross-bridge cycle will repeat. And as the cycle repeats, the thin myofilaments are pulled toward each other and the sarcomere shortens. This shortening causes the whole muscle to contract. Cross-bridge cycling ends when calcium ions are actively transported back into the sarcoplasmic reticulum. Troponin returns to its original shape, allowing tropomyosin to glide over and cover the myosin binding site on actin.
From that video, you could see that that there were basically 4 steps in the process of a contraction. Now, each one of these cycles, if you want to think of it as a cross-bridge cycle, would represent maybe 1% of the overall muscle contraction. Typically, a muscle will contract about 35 to 50% of its possible contraction strength, which means it shortens by about 35% of its overall length when contracted. But let's look at these steps again. These steps include cross-bridge attachment, power stroke, followed by cross-bridge detachment, followed by reactivation or cocking of the head group, and then we would start all over with the cross-bridge attachment. Remember what triggers the cross-bridge attachment. Because also remember here, down here is a picture that we saw previously. Notice at rest that the tropomyosin is blocking those binding sites on the actin molecule for the myosin head group. But when calcium is present, calcium will migrate into the myofibril and bind to the troponin. Now, when the troponin it's got calcium bound to it, it's going to cause a change in shape of the troponin in such a way that the troponin will pivot or allow the tropomyosin to pivot down and out of the way of the binding sites of the myosin head groups. Now, the myosin head group is sitting here waiting to bind. It just cannot bind at rest. But notice when it is ready to bind, as soon as the tropomyosin gets out of the way, it binds to that site. Once it binds, the natural thing for it to do is to go from this high energy cocked position that it has back to its resting state. This is what's known as the power stroke. And as this head goes to its resting state, it actually pulls this thin filament inward, making the contraction happen. But as it does so, it exposes a binding site back here which currently has ADP and inorganic phosphate in it. And so when that binding site comes exposed, it allows these molecules to escape. Again, this second step is known as the power stroke, and that's when we see the physical movement occur and ADP and inorganic phosphate is removed. Once ADP and inorganic phosphate are cleared out of that space can now take up an ATP molecule. An ATP molecule that would be found in a surrounding area can bind there. As soon as that ATP molecule binds to that binding site, it will cause the myosin head group and actin molecule binding site, it will cause that bond to weaken in such a way in which we will see detachment. So step 3 is cross-bridge detachment, and cross-bridge detachment is triggered by the binding of the ATP molecule. Now once that ATP molecule binds, we can use the enzyme that's found here in this head group. It's called an ATPase. And we can use that ATPase to break down ATP into ADP and inorganic phosphate. By breaking off that lyse-phosphate bond, what we do is we break the bond, and the energy that's found in that bond allows us to recock this head group, lining it up for yet another myosin head group to bind to. Now realize not every myosin head group detaches at the same time. If they did, the gain that happened from the pivot would result in just sliding back. So this is a synchronized event in which we have a variety of head groups detaching at any given time around the cylinder of that thin filament, but not all of them. So all of our gains are realized. As soon as that head group is cocked again, it can go back and it can do a cross-bridge attachment again, and we can continue this cycle as long as there is calcium available in the surrounding area To stop the normal contraction, we have to reabsorb the calcium back into the sarcoplasmic reticulum. Now, occasionally we have problems with the fact that, notice that each one of these cycles requires ATP. Well, this reabsorption of calcium back into the sarcoplasmic reticulum also requires ATP. So if I'm exerting myself at maximum level for any period of time, I could run the risk of running out of ATP. If that happens, then what will happen is I will get a cross-bridge attachment, I'll get a pivot, but remember, it is ATP that causes the detachment. So did you ever wonder what a cramp was? A cramp is when you're deficient of ATP, possibly. It can also be due to sodium and potassium, but if you're in the middle of the activity and cramp, quite frequently it's the deficiency of ATP or the buildup of lactic acid, because you can generate that ATP either aerobically or anaerobically. Also, one last thing I would want you to think about this process. What is rigor mortis? We know when somebody dies, about 4 hours after their death, depending upon the temperature, the environment they're in, they stiffen. What's going on there? Well, when the body dies, the cells become leaky. There's a lot of calcium in the extracellular space, and it can leak into the muscle cells. And when it leaks in, it binds to the troponin, moving the tropomyosin out of the way, allowing cross-bridge attachment. But since I'm dead, I have very little ATP there, and I'm not generating any more ATP after I die. So I'll get the cross-bridge attachment, I'll get the power stroke, but I'll get no detachment, and I will stiffen up. And the only thing that allows me to release that stiffness is when these proteins start breaking down as I lay there and start to decay. Now it's time for you to step back just a little bit, go back, review your muscle anatomy notes, and also take a look at this sliding filament mechanism. The next thing we're going to look at is the excitation events that go on during a muscle contraction. Been great talking to you today. Have a good one.